So let me invite our first speaker, Pasi Huovinen, and he will speak about does eta over S depend on equation of state. Pasi, please.
Thank you. And now it's my turn to thank the organizers for inviting me to give this talk. And if anyone has any questions, please don't hesitate to interrupt me. And those of you who think about the quark-gluon plasma on a microscopic level, they may wonder what I mean by my question or by my title. After all, both eta or S and equation of state, they do depend on the microscopic structure of partonic matter, of the interactions between the constituents of matter. But I'm not thinking on microscopic level, but rather as phenomenological, or my question is rather phenomenological. Does eta or S, which we extract from the data by doing fluid dynamical calculation, does the favored value depend on the equation of state we use in these calculations? And now, especially students may wonder, why do we even need to worry about that? After all, we know what the equation of state is. We know that it's given by the lattice QCD calculations. And as Fritjof told us yesterday, those calculations are pretty much under control. They are, but they haven't always been. That, for example, 10 years ago, the status of lattice QCD calculations was way different. That what is shown here is the trace anomaly as calculated on lattice using the P4 and AskData actions in 2008 and 9. By HotQCD collaboration, and as you can see, the discretization errors and uncertainties in this at the peak region, they were huge. But so at that time, what we concluded was that at the large temperatures, the lattice was reliable. So I and Peter Petretsky, we created this well-known S95P parameterization, where the hot region was a fit to lattice data, low temperature region was hadron resonance gas, and we interpolated in between. This parameterization became very popular, and therefore there's a huge number of publications where this one was used, especially to extract what the eta S is, to describe how the viscous hydrodynamics behaves. But there's been a huge progress since then, and nowadays these are the state-of-the-art lattice QCD calculations showing the trace anomaly. Gray band is the stout action result by Budapest Wuppertal collaboration. Dots are the HISC action results by HotQCD collaboration, and at fixed lattice spacing, we didn't take continuum interpolation because the discretization errors are small anyway. And as you can see, the peak has come down considerably. So equation of state by lattice is different from what we expected 10 years ago. And now there has been articles where the authors have claimed that if one uses an equation of state consistent with contemporary lattice data, actually the favored value of eta or S is larger than what we get if we use S95P. It may be larger by 25% or maybe even by almost factor 2. So we thought that, okay, finally time to update our equation of state parameterization and check whether the extraction process of eta or S really is so sensitive to the equation of state we are using. And since there have been several changes since 2009, we created a family of parameterization trying to locate which change affects the results and how much. So first, in our parameterization in our family of 4, we took the recent HISC action data and matched it to the hadron resonance gas containing the same hadrons and resonances than S95P. So this was from year 2, or particle data group list from year 2004. Next step was then, of course, take the hot QCD data and match it to the hadrons and resonances from 2018. And since there is some tension, some difference in the Stout action and Hisk action results at the peak region, we also parameterized the continuum, extrapolated a Stout action result and matched it to the latest particle data group list of hadron resonance gas, just to see that if the extracted ETOS really is so sensitive to the equation of state than what has been claimed, then we wanted to see if even this difference between Hisk and Stout actions would make a visible difference. And as mentioned, the number of known resonances has changed, but it affects the hadron resonance gas only a little bit. So the difference is basically seen here between these black and orange curves, so hardly anything. And this close-up also shows that even the most contemporary list of hadrons and resonances is actually not enough to reach the lattice result. So here around 150 MeV region, we are hardly reaching the lower error bars of the lattice data. But we still prefer to base our equation of state of hadron resonance gas in this region, because that now allows us to construct a chemical freeze out around 150, 155 MeV temperature. And it also allows us to change in the hadron cascade, if we would like to, without losing any energy or momentum. Now, if you construct your equation of state strictly on a lattice results in a 150 MeV region and make a switch to pattern cascade, if you are using URPMD, you will lose almost 10% of your energy. If you are using SMASH, then 5 to 6%. If this matters, well, that's up to you. So our task was now to figure out if the favored value of ETOS now depends on this equation of state parameterizations. How to do it? Let's think about it a little bit on a formal level. So basically, our modeling problem is that our model has a set of parameters. In the question of fluid dynamics, the initial time, initial energy density, ETOS, your decoupling temperatures, and so on, you know. And our model now converts these parameters into a set of output in the set of predictions for experimental observables, like multiplicities, average transverse moment, anisotropies, HDT radii. You make your selection of what you want to reproduce. And now our task is to find out which values of input parameters give the best reproduction of experimental output. And if we want to do this properly, we have to be able to answering what's the level of uncertainty in these values. In usual fluid dynamical modeling, we don't assign any uncertainty, and we find these favored values by simple eyeball fit. We make a large number of calculations, try find the one which looks best, maybe then iterate the parameters a little bit. But doing really systematic research is complicated. And instead of a simple eyeball fit, we decided to do a full-fledged rigorous Bayesian analysis, which basically states that now the probability that your parameter values are really the best you can have, which really lead to the best reproduction of the data, is a product of a likelihood that this calculation of yours now leads to the best output, and times the prior knowledge, what we already know where those parameters should be. Now, we decided to be very skeptical and use as our prior knowledge only allowed range of parameter values, which we can basically say that that's where the physical value should be. Say initial time cannot be less than 0, or eta was cannot either be less than 0, and based on what we know, it shouldn't be over 1/2. But within this range, we then didn't assume anything, assuming that the probability distribution is flat. Now, likelihood function. This is now where you can hide a lot of important thinking. Usually, the likelihood function in Bayesian analysis is simply the vector of the differences between your calculated and experimental result multiplied by the covariance matrix times the same vector of differences. This to the power exponential of this. So especially the covariance matrix can in principle contain a large number of correlations between different observables, but since the experimentalists usually don't give us any correlations of what the error of, say, multiplicity, how it correlates with an error, say, of B2. So we didn't include there anything either. Our covariance matrix is simply diagonal matrix of experimental errors. So our likelihood function is very close to a simple chi-squared fit. But yes. But now all we need to do would be simply to evaluate this likelihood function. But that's easier said than done. Say if you have now 8 model parameters, and you want to map what's the model output when you vary these parameters in their assigned ranges. So you might think that, okay, now you take 10 values for each parameter within its prior range. That means 10 to 8 runs. Each run takes roughly half an hour, so we don't have that computing time. So we have to take a shortcut called a Gaussian emulator. This is a stochastic non-parametric interpolation of the model. I'm not going to go into details. This simply means that we train the emulator by using 170 runs with a random model parameter values. And the Gaussian emulator then interpolates the result between different input parameter values. And then we had 30 hydro runs with other set of model parameters and compared what our emulation predicted for the result at these values, and saw that, yes, we had a very nice agreement. Not exact, but the beauty of Gaussian emulator is that it will itself as well give an error estimate for its result. So when we fold this with all the rest, we get reliable answers. Good, but still our likelihood function, even if evaluated using Gaussian emulator, is still a function with 8-dimensional domain. So evaluating it exactly is very complicated. Instead, we sample the likelihood function using Markov chain Monte Carlo. So it basically performs random walk in a parameter space. And this random walk is constrained to favor high likelihood. So basically, you are somewhere in a parameter space, you throw a dice and make a move. If your likelihood improves, you keep this move. If the likelihood becomes worse, then you throw dice again, and only with some small probability you expect this worsening of result. Otherwise, you decide to stay where you were. And when we look at the distribution of these steps the Markov chain takes, you get a probability distribution for the for your parameter values. So the steps will concentrate on a region where likelihood function is large. And now we were now approximating our fluid dynamical model with this Gaussian emulator. And our model is now 2 + 1 dimensional viscous hydro, so boost invariant, shear viscosity only so far. We are working on bulk, but we have been very reluctant in using bulk because we are not satisfied with the delta F corrections for the bulk so far. but can't avoid that. So, and then we used event average EKRT initialization, which has the normalization parameter KSAT. So no event by event fluctuations. We didn't have computing time for that. Initial time was 0.2 Fermi, fixed, we didn't vary it. And if anyone is complaining about the lack of pre-equilibrium evolution, well, what evolution do you want to have before 0.2 Fermi time? The partons are not even mass shells before that. Our initial transverse velocity was 0, and we assumed that the shear stress tensor is 0 at that time as well. So starting from a perfect local equilibrium, how good that approximation is debatable, but give us your guess what would be better. Then both kinetic freeze-out temperature and chemical freeze-out temperature were free parameters, and our temperature dependence of our eta or S was quite complicated. We assumed that below some lower temperature TH, eta or S increased linearly with the decreasing temperature, so this SHG was a slope parameter. Now, from TH on, certain temperature interval W min with the eta or S was constant. And when we are then above this plateau region, then eta or S begins to increase linearly again, and the slope parameter with slope parameter SQGP. So we ended up having 8 parameters to fit. The normalization KSAT, decoupling temperature, and chemical freeze-out temperature, those are basically nuisance parameters for our project to extract eta or S, and the temperature dependence of eta or S was then given by these 5 parameters. And then the data we wanted to fit was relatively small subset of all available multiplicities: charge particle, pion, kaon, proton, the average PT of the identified particles, and charge particle V2 as measured using 4-particle accumulants. These at 3 different collision energies, at 5 different centralities, and since at the time of we started these calculations, there was no particle identified data for the collisions at full LHC energies, only the charge particle multiplicity and V2 at that energy. RIC data by Star and Phoenix, LHC data by Alice. And what did we get? Here, the normalization parameter KSAT, right panel, the trace anomaly again, just to remind you what the difference between these different equation of state parameterization is. For KSAT, we see small difference between different equations of state, which is to be expected because entropy production during the evolution is different for different equations of state. But again, the difference is smaller than the overall uncertainty in the calculation, and in the ballpark of 1/2, which was usually used in EKRT calculations. So, folks, nothing to see here. Let's move on. Chemical freeze-out temperature, as expected, it is mostly governed by the observed particle ratios. So no matter the equation of state, we see something around 155 MeV. So everything under control here. Tiny differences between equations of state due to the overall change in the hardness or softness of the equation of state. Kinetic freeze-out temperature, again, what to be expected. The harder equation of state, the hotter your temperature. And again, the distributions are quite broad, so you could very well use one and the same freeze-out temperature for all the equations of state, and you would hardly see anything. And now the interesting part of my talk, the minimum value of eta or S. And as you can say, we could first start by thinking that yes, the earlier results in the literature are vindicated. There's a difference between the value we get for S95P and especially the the stout action fit S83. So this is what, a 20%.
Pasi,
Yes.
sorry, you have 5 minutes.
Yes, good. I'm approaching the end, as I hope you see. Good. So then note that the probability distributions are broad. So the credibility limits basically overlap. So at this point, you may say that, oops, there's difference, but it's not significant. And this becomes clearer when we look at all the other parameters. Clear. When we first were looking at this, we thought that no, this is anything but. We cannot say anything based on these parameters, these probabilities. They are broad. There's no structure. Anything goes. But then we realized that after all, the problem is that our parameterization is very flexible. At each temperature, many different parameter combinations can give us the very same eta or S. And what you see here is the favored value of eta or S as function of temperature. And those are way better constrained. So let's plot them all together to see the differences between different equations of state. These dotted and dashed curves are the favored values. And most strikingly, there's now this region where eta or S is nicely constrained and almost independent of temperature. So at the low temperature, yes, again, almost favored value almost the same, error bars quite large, 150. We start with the well-constrained region, no sensitivity or hardly any sensitivity to the equation of state. Very nicely limited, very narrow error bars. 200, almost the same thing. Well, S95P has this funny larger error to lower values, 250, and error bars begin to rise. 350, the values, favored values begin to rise. There's already some sensitivity to equation of state. 350 error bars are increasing rapidly. For 450, same tendency. Now, just to wrap this up, is that from roughly 150 MeV temperature to 220, eta or S depends on temperature hardly at all and is constrained to between 0.12 and 0.23. I prefer to say, to give you this range instead of saying that it's 0.17 plus 0.006 minus 0.05, because this range really matters something. It turned out that when we compared our result to the earlier Bayesian analysis of the Duke group, they got eta or S being 0.07 plus 0.05 minus 0.04 at 154 MeV temperature, which doesn't overlap with ours. Well, there are important differences. They used UAQMD at the final stage. They had bulk viscosity and so on. But crucially, they also had different parameterization for their eta or S. They assumed that the minimum is at 154 MeV, and from that point on, either eta or S doesn't increase at all ever, or it is monotonously increasing. Does this assumption affect our values? We wanted to find out, and the beauty of the Gaussian emulator and Markov chain random walk is that we can simply change the prior for the random walk without doing any additional calculations. So we simply constrain our W parameter to be very narrow, just 1 MeV, and constrained our TH parameter, saying where this flutter begins, again, be in the vicinity of 154, carried out the fit. And this now for our equation of state S88, which is the hot QCD result matched to most recent particle data group, hadron resonance gas. And yes, minimum value changes. The credibility limits still overlap, so these are perfectly consistent, but there's as well a clear change in the favored value. And as you can see, the favored value of eta or S is slightly different, although credibility limits still overlap. And so that's why I think that it's better to pay attention to what's the credibility limit of a Bayesian analysis than what's the favored value. Now I'm all out of time, so better to wrap this up very fast. To answer my own question, ethos depends on the equation of state, but only very weakly. The effect is smaller than the uncertainties of the analysis. So everything in the literature is obtained using S95P is still valid. Our favored value for eta or S is from 0.12 to 0.23, or for the minimum value, and this in the range of 150 to 220 MeV. Below 150 or above 250 MeV temperatures, eta or S is badly constrained, difficult to say anything. And your minimum value may depend on the parameterization, so take these credibility limits serious. Now, okay, there's still time for discussion, I hope, so thanks for your attention.
Okay, thank you very much, Pasi. So the question, there is a question in the comment box from Xiao Jiang. Please ask a question.
Okay, thank you for a nice talk. So my question is about your Bayesian analysis. So you use a MCMC method to to do a random work in the parameter space. So my question is, do you have to update this posterior probability for every steps in the MCMC you take?
No.
No.
No need. Or wait. What did you mean by probability?
No, you mean the posterior probability you calculate from your product of the likelihood function. Yes. So for every step.
Yes. So the Monte Carlo Markov chain gives you the distribution. So the Markov chain doesn't need it.
Mm.
So in that sense, yes, for every step, there's no need to update anything. So the likelihood function is given by our calculation. So the Markov chain simply moves around as dictated by this likelihood function. So no need to do any updating step by step.
But you don't have to update your posterior probability.
No, because your Markov chain gives you this posterior probability. It is what you get after your chain has taken what I don't remember how many thousands of steps. So it's the end result. You don't need it for the Markov chain to move around.
Okay, maybe I misunderstand something. Maybe I can discuss with you offline.
Yes.
Okay. Thank you.
Okay. All right. Next, Roy, please.
Oh, Pasi, I mean,
yeah.
The problem I have here is the following: that the specific viscosity, or 8/S, is a property.
Yes.
Okay. So why on earth should I have a dependence on my equation of state? It seems to me that it is a methodological problem, not a real problem. So you have a procedure where you're trying to extract 8/S, and you can't constrain your parameters appropriately. Let me give you another example. Suppose I was able to track delta F with really good precision.
What do you mean by that? I don't understand. What do you mean by tracking delta F?
Well, meaning that experimentally, so we think that delta F has some component which is reflecting the PT dependence of the viscous attenuation.
Yes.
Okay? And now all I'm saying is that suppose you can pin that down relatively well, then it means then that you don't need to know anything about, equation of state or eccentricity or anything, as long as you have a dial which you're sensitive to.
Yes.
Okay. So I guess what I'm complaining about is that I don't see why 8/S should be linked to the equation of state at all. It's a methodological problem, not a real problem.
you, in my point of view, you are now complaining about the use of fluid dynamics in general. In fluid dynamics, the evolution of your final particle distributions depend on your equation of state. So therefore, when you now try to find out the correction to your final distributions due to your shear viscosity, then in fluid dynamics, if you simply take your equation of state as given and allowed to change your eta or s independently, then I would say that your eta or s must depend on your equation of state. What we see here is that the sensitivity is so small that it doesn't matter. If we were using even old-fashioned Berg model equation of state with the first order phase transition, I would expect us to see way larger sensitivity. So I think that I tried to answer your comment in the very beginning when saying that on microscopic level, both eta or s and equation of state depend on the same processes. So we should be able to derive them both from the same processes, but so far we cannot. So in that sense, when we are doing the fluid dynamical analysis, we have to then answer, or we have to know that, okay, if we keep eta or s fixed, if we keep the equation of state fixed, does the favored value of eta or s depend on how we fix it? Again, in an ideal world, we didn't need to worry, but we are not there yet.
Okay, I just propose that we postpone this very interesting discussion to the discussion session because we need to move on. Tamas, do you have something very short question or comment?
Thank you. This is just about the dependence on the dynamics. You used the boost invariant longitudinal expansion.
Yes.
And basically our exact results in the 1+1 dimensional case suggest that the rapidity distribution has a big effect on the extracted energy densities, so the temperature and so on. So I would like to encourage you to repeat this very interesting analysis for a finite 1+3 dimensionally expanding fireball that has the realistic rapidity distribution.
I guess I have to look at your latest results, because when we have done calculations with non-boost invariant model, we haven't seen such a big difference, but I have to check what you have written.
Thank you.
Okay, all right, so let's thank our speaker, Pasi, once again. Thank you very much, Pasi.
You're welcome.
Okay, so let's move on. The next speaker is Masoud Shokri, and he will speak about hydrodynamization and the first order stable hydrodynamics.
Hi.
Hello, good morning. So you have 25 minutes to speak and then additional 5 minutes for discussions.
Okay. Okay, but I first need to share my screen. Yeah.
Oh, Pasi, you need to stop screen sharing.
I'm just trying to find out where on earth is the button for doing that. Ah, yeah. Beautiful.
Thank you.
Oh.
So. Okay. My talk is going to be about hydrodynamization in the first order causal and stable hydrodynamics versus the MIS formalism. And let me begin with the story of a lake. Imagine that you have this lake and you want to understand the properties of the collective motion of this lake. You ask your tourist friend for a theory that you can use to understand your leg. And you don't like to hear about molecules and the motions. Your friend says that, oh, so you need an effective approach. But I cannot promise you that the validity domain of my theory will be from here to here. I'm not sure about the validity domain, okay? So before your tourist friend is going to leave you, you share two observations. First of all, you say that I have thrown stones into the lake, but I have not observed anything but quickly dying waves, and I don't care about them, okay? And in your friend's mind, that means that your theory needs to be stable. And by some magic, signals in this lake cannot travel faster than a certain speed. And in your friend's mind, that means that your theory is going to be causal. So after a while, your friend come up with something like this, and she calls it the ideal relativistic hydrodynamics, and you run this code. From some initial point, you gather some information from the pump and do some measurements, and then you run your hydro code that solves this equation to understand the behavior. But there are 2 points. First of all, your results are not as precise as you like. And secondly, your friend doesn't have any clue about the initial point. And she's surprised by the fact that you can run your code very close to the pump. This picture is a cartoon of what happens in the heavy ion collisions. We know that from both theoretical perspective and experimental data, that the explanation of heavy ion collisions data requires a dissipative theory of hydrodynamics, not an ideal. And the most general form for the energy momentum tensor of an uncharged fluid is in this form. But there are a problem, and there is a problem, and the problem is that if you assume that your hydrodynamical variables are the temperature and the flow velocity, they cannot be uniquely defined beyond the zeros order. So you open your Landau-Lifshitz book and you find that there's a prescription for that. It says that you need to fix the frame, which is like this, and you need to eliminate any term that is of second order when taken on the equation of motion or on-shell. Okay. However, from long time ago, we know that the Landau-Lifshitz theory is neither stable nor causal, and it but by the first one, it's not instability, we mean that the equilibrium is not actual. There's no physical equilibrium in this theory. And excitations can propagate faster than light. So what we do? There is something else, Muller-Stridler-Stratt theory. The prescription is as follows. You fix the frame similar to the Landau-Lifshitz or Eckart theories, but you promote the dissipative fluxes to dynamical variables and write dynamics for these new variables. So you're expanding the number of variables into hydrodynamics. And as Shipu and friends shows in 2009, these relaxation times with this color here that are introduced by Muller-Stridler-Stratt are not arbitrary. And state-of-the-art hydro simulations are based on not these vanilla MIS equations, but on enhanced versions of these stories, such as DNMR, which is used in the music code. For example, if you take the music code, you need some initial condition. You have these equations, which are quite complicated, and you run your hydro code from some initial time. But again, as in the lake story, there is a problem for the tourists that your initial time is much smaller than predicted by macroscopic theories. We call this initial time that works the hydrodynamization time. Now, is the MIS the only thing that we can do? Until 2017, the popular belief was that any first order hydrodynamics is unstable. However, as these works showed, we can make a first order stable and causal theory by expanding the number of transport parameters instead of introducing new dynamical variables. I'm going to assume a conformal uncharged fluid for simplicity. And the prescription now is as follows. You add any term that is first order and derivative and respects the symmetries of the theory. You do not fix a frame, and you do not remove the official terms here. Then you end up with this T mu, okay? And on the conditions that is showed here, your theory will be stable and causal. When we encountered these papers, we had our doubts like anyone else. So we thought, let's solve these equations in the simplest case that we know, which is a conformal Birkenflow. We as theorists love Birkenflow for different reasons. First, there exists a particular coordinate system, which we call the Milnor coordinate here, in which the fluid is at rest, but the space-time is expanding. Second, the equations of motion are one-dimensional ordinary differential equations. And third, this pressure anisotropy is very easy to find. And you have an ideal hydro exact solution and also an exact solution in the Landau frame. So what happens when we use MIS or FOCS? In both cases, you end up with a nonlinear second order equation. And as many areas in physics, you can write a power series solutions. And this lambda is essentially a scale of dimension of mass. And this solution in both cases is a divergent series, but an asymptotic one. And you know that divergent series are not as bad as people think, as far as they are asymptotic. But there are differences between these two solutions, between these two theories. First of all, the entropy current in the MIS theory contains second order coefficients, like the relaxation time. And they do not violate the second law of thermodynamics. But in the FOCS stories, the official parameters that you have put into the theory to make it stable violate the second law. Coughton argued that you should use power counting to preserve the second law. But let's not do that and find the final entropy distribution, which is actually a physical observable. This term is similar in the Landau frame and the FOCS theory. This red term is not in the Landau theory. Okay, but if we buy the argument by Coughton, this term doesn't matter. You should put it to 0 by hand. This is the first thing that I want to emphasize. And I come back to this issue at the end. And the truncated series is like this. Okay, you have some blue terms that are not present in the Landau-Lifshitz story. And you can try to match this story, this late time expansion, with the results of any microscopic theory that you got. For example, you can match them with n equal to 4 super young meals. And you know that in the MIS formalism, you can do that to find a value for the relaxation time. However, here, if you match the first order term here, you find this result, which is the case's limit, and it is anticipated. But the second term cannot be matched unless you violate the stability. So this is a problem, because if you want to do a simulation, you need some clue about this value, okay? But you cannot find anything from microscopic theories. Also, the pressure anisotropy here is independent of the offshell parameters, and it does not provide a way to understand hydrodynamization. So how we understand the hydrodynamization? Heller and Spaninski in a seminal paper in 2015 showed that if we reformulate the MIS equations in a certain way, which this functions, we can find that all arbitrary solutions quickly decay to an attractor. By other terms, the nonlinear equation of motion in MIS formalism forgets the initial condition. Okay, the prescription is as follows. You write the equations in terms of this function, which is of a function of this variable, is dimensionless time, and this is related to pressure anisotropy. So F equal to 2/3 is where you have ideal hydrodynamics. You write the equation of motion, you expand the equation of motion around W equal to 0 to find this initial condition. And then you compare the solution from this initial condition to any arbitrary initial condition. And you will see something like this. This purple line is from this initial condition, and these guys are from arbitrary initial conditions, and you can see that all of them are decaying very fastly to this purple line, which we call the attractor. So this, we already knew that the same prescription with F works for the conformal FOCS, but what is the physical significance of F in this first order theory? I already said that this F is not related to the pressure anisotropy in this case. Also, we want need to inspect the analytical structure of the Borel transform series, which I'm not going to talk about. We found that this F here is related to damping of the offshell parameters. So we use the same prescription again. And here is the attractor, okay? So you can see an attractor again in this story, but there are some crucial points about these attractors that were not present in the MI's case. First of all, something that is somehow disappointing is that the smallest system that the FOCS can describe is 60% larger than the one in the MI's story. Then there is a very crucial point. As I said, the Coughton argument is if you write d mu s mu, you need to take into account the power counting. Your tool is first order, so you don't you erase anything after the first order, and this guy will be positive. Okay. However, let's forget that. Let's assume that there is a hypothetical system that from the very first moment described by the FOCS hydrodynamics. And this is not, we are not using the power counting here. Okay. This is the unstable solutions. As you see, in unstable solutions, the second law of thermodynamics is always satisfied. But in stable solutions, you can see that in very early times, the second law is violated. However, this is not a bad thing. It's actually the reason that this story is stable. Because if you assume a state here, this state have always a larger entropy than a similar state in this unphysical region. So it cannot run away to that region. So this state is always stable. And the maximum entropy is at infinity. So your equilibrium is the state that have the maximum, absolute maximum entropy. This is not the case here, which is very similar to the Landau theory. And as a result, and in contrast to the MIS, you never have a reheating effect in the stable attractors. From the first point, you can see that the temperature is decreasing. But if you use unstable parameters, you will have a reheating. And if you have seen the literature on the MIS, you can see that the pressure is negative. The longitudinal pressure is negative at early times, like here. But if you use the stable parameters for the first order stable hydrodynamics, the pressure is always positive, and it's going to be isotropic in late times. So I have some final remarks. And first of all, our calculations were based on the conformal symmetry. And actually, there is no rigor argument about emergence of attractors in non-conformal system. This is a very big question to theorists to investigate. Also, I have to tell something else, that we have seen attractors in the Bjorken and Grabser flow. Both of these flows are highly symmetric. They have at least 3 spatial symmetries. And if you get back to this story, to this formula here, you can see that this term cannot exist in such highly symmetric flows. So a very important question is, what happens in less symmetric flows? We have tried the exact solution, the 1+1 exact solution of hydrodynamics by Professor Chorgu and others. From the February, we had some preliminary results that suggest that attractors exist also in that case. However, the problem is actually very hard to solve, because you cannot find something like a late time expansion, and the definition of F and other functions that may be used to find the attractor is not trivial. Another question is that what happens in the magnetohydrodynamics? Are there attractors also in the magnetohydrodynamics? Also, we have some preliminary results that for poorly conductive fluid, and again in the Birkhoff flow, the magnetic field decays to an attractor. Another question is very crucial, because people ask if this first order theory can replace this the MIS formalism. This needs us or other people to do numerical simulation based on FOCS, for example, in 1+1 or 1+2 setups, and see what happens. But we have a lot of parameters in this theory that cannot be fixed easily. So this is a big problem for the hydro practitioners. I wrap it up here, and I'm ready for questions. Thank you for your attention.
Okay, thank you very much. Now the session is open for questions and discussions. I see nothing in the chat box. Aha. Peter, please.
Okay, hello, Masoud.
Hello.
I'm interested in that you consider the Müller-Isler-Stewart theory as an exemplary one, as far as I understand. So some good properties. Why?
I didn't hear it well. Sorry, can you repeat?
Do you hear me better? So my question is that why? So the Müller-Isler-Stewart theory does have some unreasonable, let's say, not physical properties in my mind. For example, the stability you praise is only for the linearized version. So do you think it is a theory that we can trust more than the new official instable versions?
First of all, I need to address the first thing that you said, that the nonlinear stability of MI story is proven by Visconti and others in this year. I can provide you this. In the London-Lifshitz frame, I think.
And the symmetricity is also proved?
No, there is no,
otherwise it's nothing.
Without any symmetry. In general case and coupled with Einstein equations.
That's okay.
So this is a work, and I will put it on in the
That's
chat.
another discussion, I think. So you trust that that's the point because of these proofs. Okay, all right. Thank you.
Okay, thank you. Then the next is Saren, and then Tamas.
Yeah, hey. So I wanted to ask, I had two questions actually. So one of them was about so this new transport coefficient essentially that you said you introduced. So I was wondering whether there's a I think this was CP basically, whether there's a Kubo relation for this kind of transport coefficient, because usually, I mean, as far as I know, there's only like 2 first-order transport coefficients that you usually get Kubo relations for. Or is this effectively like a higher order transport coefficient? So that's my first question. And the second question is what is in both of these theories, or in this Fox theory, what happens when in the Bjorken flow, when time goes to 0, what happens with the longitudinal pressure there?
The first question, at the moment, we do not have any microscopic understanding of these new transport parameters, but there are people that are working in this direction, and I'm not one of them, but I have heard from different people that have some ideas they are working on. But as far as we understand right now, these transport parameters are just regulators, like the cutoff that you put in the effective field theories.
Okay. Yeah.
And the second question was about
about the behavior of the so longitudinal pressure to pressure anisotropy as you go W to 0 in Bjorken flow. What happens there for the Fox attractor?
It's here. The longitudinal pressure for the FOCs, for the stable choice of parameters, is like this at initial times.
Okay, so it depends on the transport parameters.
Yes, this is exactly okay. This red line is the critical value, CP equals 1, and these are for CP smaller than 1 that makes the theory unstable. This is similar to the MIs. But this is not.
Can you choose the parameter such that it goes to 0 actually?
No, it seems. Yeah, you can choose a parameter that is unstable and it goes to 0. But if you choose a parameter that it makes your theory stable, it's always larger than 1 because the critical value is 1.
Yeah. Okay, thanks.
Thank you for it.
Thomas, please.
Thank you for this very interesting talk. I wonder if you have only one attractor or maybe there is a range of attractors. Gábor Kasza will talk about new results in exact solutions of dissipative hydro, where we find that actually we have the perfect fluid solutions as the attractors. So the dissipative effects cancel for late times, and it's pretty general, much more general than the first solutions that are available on the web already. And I wonder if in your case, for example, maybe you can show this line that you had the first one when you had the attractor. So in our case, the attractor is the perfect fluid solution, but the parameters of the perfect fluid solution can change. So there could be different attractors.
In this story, there are not, because, for example, you can see it here. There are 2 solutions from the slow roll approximation that one of them is not unphysical, and the other, it is the only one that is physical. And it was actually a question that we looked for, but we didn't see any other attractor. However, in the 1+1, actual 1+1 dimensional theory, there seems to be 2 functions that you need to define to find the attractor. One is related to this term, and the other one is related to this term. And we find in your flow that both of these guys show an attractor behavior, but it is very hard to find the exact, I mean, it's very hard to solve the attractor. We have suggestion of existence of these attractors. I have not put the results here in the back of the slides, unfortunately. I forgot.
A simple way to ask the question in other way is that in your case, the perfect fluid solution would correspond only to one line, or it would have parameters like the initial energy density.
Yeah.
So we only one.
Yes.
So is it the attractor?
It is actually not the attractor. The attractor will go to that limit.
Yes, yes. Okay, thank you.
This is exactly
this was the question. Thank you very much.
You're welcome.
Okay, all right. Okay, so let's thank our speaker once again. Thank you very much for a nice talk. Good, so let's move on. Let me invite the next speaker, Aditya Nath Mishra. Are you there? Okay.
Yeah.
So please start the screen sharing, and he will speak about study of degrees of freedom in dense QCD matter using color string percolation model.
Okay.
Please.
Yeah. Hello, everyone. So in this talk, I will show my results of an analysis of Alice proton-proton and lead-lead collision using this color string percolation model. This work is done in collaboration with Gipaik, Pahara, Sharenberg, and B.K. Srivastava. So initially, I will give a brief introduction of this color string percolation model in 1 or 2 slides. So multi-particle production at high energy is currently described in terms of color string stressed between projectile and target. And these strings decays into new ones like Q bar pair. And then finally, they produce these hadrons, which are detected by the surrounding detectors. And this particle production mechanism is 2D Swinger 2D mechanism. In percolation model, as number of string grows with energy, this number of string grows with energy, or if you increase the number of participants by changing the colliding species, then your number of string increases, and they start to interact and overlap in transverse area, as it happens in the 2D disk percolation theory. So in percolation theory, this one important parameter is this zeta parameter, which can be defined by the given function, where ns is the number of strings, Sn is the single string area, and Sn is the total number of overlap, total nuclear overlap area. So this zeta parameter, I will give a bit more introduction of this zeta parameter in a further slide. So what is happening in deconfinement? Actually, in deconfinement, and these quarks and gluons becomes free, and like if you have very high temperature or density, then there is no feasible boundaries between these quarks and gluons, and so you cannot make partition into color neutral hadrons. So they say they are deconfinement. And in what is happening in color string percolation model, so we make a cluster in this model, and this clustering is very similar to the deconfinement, because in cluster we have no specific boundary for these strings. So in this model, where the density where this percolation cluster starts to percolate between the strings is known as the critical percolation density, which is 1.18 is calculated from the model. So and this, as I told in the particle production mechanism is the Swinger mechanism. So in this model, we can give the multiplicity by this formula, this mu1 equal to f zeta n mu1, where this n is the number of total number of strings. Mu1 is the number of particles produced by this a single string. And this f zeta parameter, we can get this number from data. So I will show you how we can get this f zeta parameter to calculate the multiplicity in this model. And then we can go for this transverse momentum calculation, where again we have this f zeta parameter. So if we can get this zeta parameter from the data, then we can calculate the other thermodynamics observable also. And this f zeta parameter is directly related to this critical density, percolation density, by this formula. So in the further slide, I will show the results for the Alice data for PP and lead-lead collision, we calculated this temperature, energy density, and degree of freedom using these data sets. So how we proceed with this? So first, we need a reference data. So reference data means where percolation doesn't exist. So we have taken this star proton 200 GeV data, and we have fitted this power law function to this data, and we get this P0 and N parameter from there. And then we just parameterize this formula for gold-gold collision, this below formula. And we use this same parameter P0 and N from which is we got from this reference data, star 200 GeV. So here f zeta pp is this colors, this number is for pp, and this f zeta gold for gold. So if there is no percolation, then your f zeta will be 1. So like as I have taken the reference point where there is no percolation, so then my f zeta pp will be 1. Now if I fit this function to my heavy ion data or high multiplicity pp data, then I can get this f zeta parameter. So if I get this f zeta parameter, then I can go for the further calculation. So in the Swinger mechanism, this particle spectra can this exponential function, and in the thermal distribution, we have this distribution. So as we know, there is no fluctuation involved in this Swinger mechanism, but if we introduce this string tension fluctuation in this, and then we can compare with this thermal distribution, then we can get the temperature, this expression for this temperature. And if we simplify it in terms of this f zeta parameter, then our final temperature expression will be this under root of mean pt square divided by 2 f zeta, where this mean pt 1 square is actually not transverse momentum as in experimental we observe. It's basically the string tension, single string tension, which is a fixed number in this model. So now our this temperature is directly related to this f zeta parameter. So now we have f zeta, so we can get the value of temperature. So before going to our result, we have just give a small check for this model. So what we have done here, so we have plotted this percolation density parameter f zeta as a function of number of participants pair. And you can see these solid symbols. So blue one is for lead-lead 2.76, and red one is for the lead-lead 5.02 TeV. So you can see this as your number of participants increases with them, and then for the higher value of n part, it almost gets saturated. It's a similar behavior as we observed for this charge particle multiplicity, which is shown here by the open symbol, and the axis is right hand side axis, dn charge by d eta scale by number of participants. So this our percolation density parameter has a similar kind of behavior as we observed in experiment. This number, this dn charge by d eta number. So after this, as we have the f zeta number from our model, so we just calculated this temperature, the lower plot. So you can see I have shown here the PP 13 TeV, lead-lead 2.76, and 5.02 TeV. And you can see it's almost shows, if I take 5% error bars, then within 5% of error bars, statistical errors, this are on the same line. And the interesting thing is that you can see this dotted line, which is universal hydrodynamization temperature. So even for the very very peripheral collision, or you can say the very small multiplicity in 13 TeV, the temperature is higher than this universal hydrodynamization temperature. It means we have for a very low multiplicity in PP, or very peripheral collision in lead-lead collision, we have this deconfined state of quark and gluon. So at this high temperature, and the upper plot is the color suppression factor. As I told you that we calculated from the model, so it has again this decreasing behavior as a function of anthrax, and they have again very small difference in like it's like a band within 5 or 10%, you can say. So then we go for the energy density calculation. We have used the Bjorken formula for this calculation, and so here this in Bjorken formula, this tau pro, which is basically is a QED production time for a boson, which can be scaled from QED to QCD, and it can be given by this formula, and we just put this tau pro values in expression of energy density, and we calculate this energy density. So the interesting thing here, again, for the energy density, you can see that upper plot is for proton-proton, and the lower plot is for the heavy ion, like gold 200 GeV, lead 2.76, 5.02, and xenon 5.44 TeV. So interesting behavior is that like whole plot can be divided in 2 sections, even for PP and heavy ion also. So initially, as we increase this percolation density parameter, our this energy density increases linearly, but after a certain point, which is actually about value 4, so this linear behavior is deviate from the linear behavior, and it's happening both in PP and lead heavy ion collision.
Aditya, you have 2 minutes.
Yeah, sure. Thank you. So before going to my last plot, so I have just shown here the lattice simulation result. So here this energy density, entropy, and pressure is plotted as a function of temperature. So I just concentrate on this energy density plot. So you can see that the energy density increases with the temperature, and it shows almost saturation behavior, gets trying to saturate with this temperature, but it never reaches to the Stefan Boltzmann values. So if we have this energy density by T4 values, then like if we talk about this 2-flavor QCD, then we can calculate this degree of freedom. We can get the number 37 if we have energy density values is 12. If we talk about the 2+1 flavor QCD, then we can highly reach at 47 degree of freedom. So this is our energy density plot as a function of temperature. So you can see that our result agrees with this lattice result up to about 220 GeV. But after 220 GeV, we have a strong deviation, a strong rise in our energy density by temperature plot. And if we try to get the degree of freedom from this number, then we have a degree of freedom 47, which is for the ideal gas for the 3-quark flavor. So we try to understand this part, and to give the explanation of this, we have this reference from Castorena, Gavai, and Sad's paper, where they have 2 plots. So let's talk about the left one, which is basically 2-state. So as the temperature increases, your entropy increases, and after this your deconfined temperature, it almost gets saturated with this temperature. But the right hand side plot says that when your temperature increases at this deconfinement boundary, you have this deconfined quark, but they are dressed with gluons. But now if you go for a more higher temperature, then at a certain temperature your this dressed gluons gets evaporated, and you have now the confined state of quarks. So this basically, which is quark gluon plasma. So this kind of this sudden increase we also observe in our energy density plots. So now I will just summarize it. So the clustering of color sources produced by overlapping strings has been applied to both heavy ion and proton-proton collision. And the most important quantity is in this picture is the multiplicity dependent interaction area in this in the transverse plane, and the temperature from heavy ion and track divided by this scaled by the overlap area. And our results agrees with the LQCD results up to temperature 210 MeV. And above this temperature, we have a strong rise we observe a strong rise in energy density by T4 value, which gives our degree of freedom 47. And we observe for the first time a two-step behavior in the increase of degree of freedom. So thank you very much for your kind attention.
Okay, thank you very much. Okay, question. We have a time to take one short question. Okay, Tamas, please. Tamas? Okay, he's absent with keeping his hands up. Okay, so
pardon, this was just an accident. I am here, but I left my hand up. Sorry. Sorry.
Any question, by the way? You can take this opportunity.
Please leave it to others.
Okay. What's your plan to possibly extend or improve your model? And also the similar related question: do you have any conceptual or technical difficulty to apply your methodology to high baryon density region?
No, I don't think so. We have any difficulty to apply that. Actually, we have planned first to see this event by event analysis, because we have in lead-lead collision, we have a sufficient number of particles in each event. So it's better to see, because in the collective events, sometimes we cannot conclude anything. Sometimes I got this comment that if you say take 0 to 5% centrality, you have all type of events in that centrality, so you can't conclude anything. So we have a plan to see this behavior in event by event analysis for the lead-lead collision in future. So
okay, good. It's on your agenda. Okay, thank you very much. So let's thank our speaker once again. Thank you for a nice talk.
Thank you.
Okay, so the next speaker, Clemens Werthmann. Are you there?
Yes, good morning.
So he will speak about description of non-equilibrium dynamics in PP and PA collisions.
Does everything seem to be working?
Yes.
Okay. Thank you very much for the opportunity to speak here. So I will talk about the linearized kinetic description of non-equilibrium dynamics in PP and PA collisions, which I've been working on together with my supervisor, Sören Schlichting. So first, let me explain what kind of physics we are interested in. Generally, we want to describe the QCD fireball created in a particle collision, and more specifically, we want to examine how spatial anisotropies in the initial state described by the eccentricities epsilon n dynamically create momentum anisotropies in the final state measured by the flow harmonics Vn in small systems. So as you know, the fireball tends to expand faster into the directions that it initially had a smaller spatial extent in, and in hydrodynamics, this is explained with a larger pressure gradient. But in small systems, when the densities are too small and the gradients are too large, hydrodynamics should not be applicable. So instead, we need a microscopic description in terms of kinetic theory, where we need to explain the momentum anisotropies just via very few scatterings per particle. And actually, numerical transport codes simulate these dynamics quite well, but they do obscure part of the mechanism of how they are created. So we want to accompany these transport codes with an analytical treatment of the problem for a better understanding and maybe to find parametric dependencies. So how does the microscopic description of the fireball work? The most basic object is the phase-based distribution of produced particles, and in our case we are restricting ourselves to describing only on-shell gluons. So we have only this one phase-based distribution. Additionally, we are assuming boost invariance, meaning that the phase-based distribution will depend only on the difference of y minus eta, which reduces the dimensionality by 1 for 2 plus 3 plus 1 dimensional description. This also means that our final observables will have to be expressed as constant densities in pseudo-rapidity or ratios thereof. The time evolution of the phase-based distribution is given by the Boltzmann equation, which has the change of f due to the particle motion on the left-hand side and the change due to the scatterings encoded in the collision kernel on the right-hand side. And we will solve this problem both analytically and numerically. And in the following slides, I will show you results of both cases. First, let's look at the analytical description. If we want to solve the Boltzmann equation analytically, then we have a problem because of this collision kernel. It is a functional of f, meaning that this is an integral differential equation, which often does not have an analytical solution. So we need to make some approximations in order to find a solution. And there are several approximations that we are doing. The most important one is making use of the fact that we are describing a small system with very few scatterings. So we might try to expand the solution in the number of scatterings. Such an expansion is called an arithmetic expansion. So in this regard, actually, this is kind of the opposite of hydrodynamics, because hydrodynamics works with the limit of infinite interactions, whereas here we are expanding around the limit of no interactions, where in zeroth order the particles are just freely streaming, and then in first order we calculate the change of f due to the first particle scattering, where the scattering rate is computed with the zeroth order result. So in this way, this is just an inhomogeneous version of the same PDE as before. So this is quite easy to solve. And in principle, we could keep going, but we stopped at first order. The next simplification is in the initial condition, where we assumed an isotropic Gaussian energy density, to which we add a small anisotropic perturbation on top, in which we then linearize our equations. The final simplification is a simplified model assumption for the collision kernel that we actually hope to be able to drop later on. So this is the relaxation time approximation that just assumes exponential relaxation to local equilibrium. And in our case, the relaxation rate is that of a conformal system. So if you're looking at this closely, you might already expect that the build-up rates of our observables will depend on some opacity parameter, gamma r, that should very roughly speaking be something like the inverse of this relaxation time. And you might also assume that this might then be something like the expansion parameter of this arithmetic expansion. And what we found is that such a parameter with these properties does in fact exist. So now I'm showing you some plots of the analytical results. This is the transverse energy weighted and particle number weighted V2 per epsilon 2 and gamma r as a function of proper time tau in units of system size r. So you see that the energy weighted case is already fully determined due to the fact that our initial condition was defined on the basis of an energy density, whereas in the particle number weighted case, we have an additional parametric dependency that tells us how much energy per particle is in the system as compared to how much there should be in equilibrium. But in all cases, you see that most of the buildup happens around tau over r equals 0.5 to 2. In particular, the system needs some time in the beginning for the anisotropy conversion to kick off. And another thing to notice is that for the additional parameter dependence in the particle number weighted case, there might be some cases where the loss term wins in the end and V2 actually goes down slightly for large tau. And another thing that I wanted to show you is this heat map of the production of V2 as a rate in tau and density in experp. And here you can see that there's actually two regions with different sign of the contribution to V2. And another thing that you see is that actually the important region for V2 production ranges quite far into the outskirts of the system. So this is something that we are currently still examining. Next, let's look at the numerical simulation where we can drop the linearities. We wanted to employ this numerical treatment of the exact same problem in order to find the range of validity of our linearizations, and also to have a nice tool for quickly checking for more interesting observables. But of course, we need to reformulate our problem a little bit so we can put it on the computer. And the first thing that we did is we switched from describing F to describing only moments of F, which are these momentum moments weighed with spherical harmonics and p tau. And the fact that we chose to weigh this with p tau means that we are now describing only energy-related degrees of freedom, meaning that in the end we can also only extract energy-related observables as linear combinations of these CLM or ratios thereof. So for the momentum discretization, we can now quite straightforwardly just cut off this expansion at some finite Lmax. And for the transverse space, we just employ a lattice. Now, of course, we also need evolution equations for these moments. And to find those, we can just take the same moment of the Boltzmann equation. But now, since there's different momentum components showing up in the equation, we will get additional dependencies on the momentum angles, which will yield some linear combinations of the spherical harmonics. So we end up with this system of coupled differential equations that we have.
Clemens, you have 2 minutes left.
Okay, so here is the numerical results. First, I'm showing you the same plot as before, where the analytical result is now in black, and in colors, I'm showing you the numerical results for different opacities. As you can see, the smaller our opacities are, the closer we get to the analytical result, which is a nice confirmation. We also found varying epsilon2 that there's no significant deviation from V2 being linear in epsilon2, which is not plotted here because you didn't see much. And then also I've plotted the opacity dependence of the final values of V2, where you can see some saturation sitting in for very large opacities towards some finite limit. And for small opacities, you see that the numerical results become nicely tangential to the analytical one, and stay kind of close for a relatively long time. Okay, so in summary, we have employed a successful analytical computation of the observables to linear order in opacity and eccentricity in RTA. Our numerical results match the analytical ones for small opacities and are always linear in eccentricities. we have found that for the buildup of V2, the alter regions are of non-negligible importance. And for the future, we want to closer examine this V2 buildup, also with our numerical code. And we want to check for other new interesting observables. And further down the line, we hope to be able to switch from our RTA kernel to a more realistic QCD collision kernel. Thank you for your attention.
Okay, thank you very much for a very clear talk. Okay, questions? Does anybody have a question in the audience? Anything in the chat box? No. Mark, please.
Hi. So
Hi.
when you say that your numerical results are linear in eccentricities, I mean, is that by construction? And if so, would the same happen if you go to, for example, V4 or higher anisotropics?
It is not by construction. It might depend on the form of the initial condition, which so the general form was fixed for the runs that we've been doing. I expect that the linearity will also be there for epsilon 4, but we can't actually do runs with epsilon 4 because of the lattice and transfer space, which so there are some numerical problems that mean that there's always some epsilon 4 in the system, even if you don't put it in, because the lattice is square shaped.
Okay, next question from Roy, please.
Yeah, can you go, I think it might have been slide 4, but there were several after, which, you know, why is your value, I mean, am I missing? Oh, I guess maybe you're scaling. I was gonna ask, it seems like the values of your V2 is pretty large. I mean,
yeah.
Is that just because you artificially make the system opaque or what?
This might be due to the fact that I'm scaling with this opacity parameter.
That's what I'm realizing after. I had missed that the first time.
Mm.
Do you have the unscaled ones?
Yeah. I mean, you can also look at the numerical result. Yeah. This is unscaled.
Is this scaled? But this is also scaled, so yeah.
It's scaled with just eccentricity, but not opacity.
And where do you get that eccentricity from?
Well, we put it in the system via our initial condition.
Oh, so you just okay, I see. Mm. You give it an eccentricity.
Yeah.
Yeah. Okay.
Okay. Thank you very much. So I see no further questions. So let's thank our speaker once again. All right. So our the last speaker this session, Gábor Kasza. Okay. Are you ready? Okay, good.
Yes, I'm ready. Can you hear me? Can you see me?
I see you, yes, and then I hear you very clearly. And he will speak about new solutions of relativistic dissipative hydrodynamics. Oh, you have 15 minutes to speak.
Yeah, okay. Can you see my slide?
Yes.
Oh, very good, okay.
But please make it full screen.
Of course.
Oh, yeah, okay. So please go ahead.
Okay, so thank you for the introduction, and let's start the outline of my talk. So I will provide new exact solutions of relativistic Navier-Stokes and also Israel's QR theory. And in the part I will focus the spherically symmetric Hubble flow. We use this velocity profile, and you will see that it provides great amount of freedom of dissipative coefficients. In the second part, I will speak about the asymptotic behavior of these new solutions, and we will check the effects of the dissipative coefficients in the final state measurements. And in the last part, I will show two applications of the new solutions. One is an indirect description of experimental data, and I will speak about that how we produce the new non-relativistic solutions. Okay, so first, just quickly, here are the basic equations of relativistic hydrodynamics for the Navier-Stokes theory. So you can see the local conservation of force momentum and particle number. Here is the energy momentum tensor, the heat current, and the last is the term which describes the viscose effects. Here, eta is the shear viscosity, and zeta is the bulk viscosity, and this capital pi is the bulk pressure. And if I switch to the Israel-Stewart theory, you can see the change in the last line. So we have an additional term in the bulk viscosity, which includes this tau pi relaxation parameter. So to close, if we want to solve this equation system, we need the equation of state. And we use a very simple equation of state, the proportionality between the energy density and the pressure, and the proportionality factor is kappa, which related to the speed of sound. And in this work, we use constant kappa, so actually we can use an average speed of sound. As I said, we have found a Hubble type solution, so we use the Hubble type velocity field. And here is the velocity profile that we have used. And if we have a velocity field, we can solve the scale equation. We wanted to find the scale variable because we wanted to find the self-similar solutions. And we have found directional scale variable, you can see here, which means that we could satisfy the scale equation separately in every direction. And so because of that, the solutions that I will show you, these are multiple solutions. Okay, so because of the Hubble flow, these are the differential equations that we had to solve for the Navier-Stokes and the Israel-Stewart theory. So we have the continuity equation, the energy conservation. The Euler equation is reduced in both cases to a simple condition where this phi and the psi function are arbitrary functions of the proper time. In the Israel-Stewart theory, we have an additional differential equation for the bulk pressure. In both cases, of course, we have the entropy equation, which ensure the entropy production. And we use the different ansatz for the bulk viscosity in the two cases. In the case of the Navier-Stokes theory, we assume that the bulk pressure is proportional. The bulk viscosity is proportional to the pressure, and in the Navier-Stokes theory, we assume that the bulk viscosity proportional to the bulk pressure. If this tau p relaxation parameter is 0 or pi is constant, so the time derivative of that is 0. From the Israel-Stewart theory, we get back the Navier-Stokes theory. So this is the connection between that. And what is very important in this slide that you can see in the equations the coefficient of the heat conduction and the shear viscosity. These two coefficients is cancelled from the equation because of the Hubble profile, because of the Hubble flow. Okay, so quickly, I'll show you the analytic solutions of the Navier-Stokes equation with constant kappa, as I said. So we solved it for two different cases, when we have conserved charge and when we have no conserved charge. In both cases, we have a general form for the pressure and the temperature. So what is the difference between the two cases? The difference lies in this TA, asymptotic temperature constant. It's called the asymptotic perfect fluid initial temperature. So you can see these are constants, and this is the main difference between the two cases. And I will show that how important is this parameter 2 or 3 slides later. But first, let's see this nu and tau functions are the functions of the scale variables, and this is what includes the coordinate dependence of this these solutions, and these are arbitrary functions under these conditions that tau is equal 1 over nu. Okay, so just for the record, I also show you the analytic solutions of the Israel-Stewart equations with constant kappa. The first function is not the back viscosity, it's the back pressure, of course, sorry for the mistake. So we have the back pressure, we have the pressure. So from these two functions, we can give any of the other thermodynamical quantities. And here are the constants. And what is very important that you can see that this another asymptotic constant parameter appears here, the asymptotic pressure. So yes, okay. So let's move on. What is this asymptotic constant? So if we take the limit when the tau is much greater than the initial proper time, both cases, the Israel-Stewart and the Navier-Stokes case, lead to the same asymptotic perfect fluid temperature profile and pressures, and of course it will be same for the entropy density too. And these asymptotic perfect fluid profiles actually are already found by Csörgő, Csernai, Hama, and Kodama. So in this paper, they provide perfect fluid relativistic solutions. And you can see that these functions has perfect fluid forms. So the effect of, you can see the effect of the back viscosity, because the effect of the back viscosity are absorbed by these normalization constants. And you can see here, for example, this TA, the asymptotic temperature. Here is the effect of the back viscosity, so the initial back viscosity. And so because we can say the effect of back viscosity is scaled out. The effect of back viscosity rescale the temperature, rescale the pressure, and rescale the entropy density. Okay, but let's see this effect in figures. So first, I just show two very simple figures. At the left side, the solutions of the Navier-Stokes equation, and the right side, the solutions of the Israel-Stewart equations. So here, every line starts from the same initial conditions, and the black line is a perfect fluid solution. This is actually Csernai, Csörgő, Kodama, and Hama solution, and the colored line are our viscose solutions with the different back viscosities. And you can see that because of the entropy production, the temperatures are heated up. So it's works well. Okay, but let's see what happens if we have a fluctuating initial conditions. In this case, the black line is the perfect fluid asymptote. It has the same form what I have shown in the previous slide, but it's not starts from the initial temperature. It starts from the perfect fluid asymptotic initial temperature. And this asymptotic initial temperature is a mutual parameter of the colored lines. These colored lines, again, are viscose solutions. And you can see that if we go to the limit when tau is great, then all cases approach this perfect fluid asymptote. So actually they have the same asymptotic behavior. They approach a perfect fluid solution, actually. Let's see the first applications of the solutions of the Navier-Stokes equations. In the right-hand side, you can see...
For interruption, Gábor, you have 5 minutes.
Okay, thank you very much. Okay. So in the right-hand side, you can see a fitting. So the dots and so the data points are the different flow coefficients for different centralities, and the lines are the fit. So it is a theory. It is a perfect fluid relativistic hydrodynamic solution. And this theory had two fit parameters, the final state parameters, the final state temperature, and the final state proper time. In the left-hand side, this is our figure. We reproduced this final state, which describes these experimental data. And you can see that we could reproduce this final state with a perfect fluid solution and with viscous solutions with three different viscosities. So actually, we could describe the data with perfect fluid and also with viscous solutions, because the main point at the final state approaches the perfect fluid solutions. Okay, some further applications. It is actually a second application. I show you how we produce the new dissipative solutions of non-relativistic hydro. The first step was that we take the non-relativistic limit of the relativistic Navier-Stokes, the relativistic solutions of Navier-Stokes equation, and we have found a spherically symmetric solution of non-relativistic dissipative hydro. The second step, that we generalized the previous solution to ellipsoidal symmetry, and the first step, that we add rotation to the velocity field. As a result, we have found an ellipsoidal symmetric rotating dissipative fireable solution of non-relativistic hydrodynamics. And I just quickly, just for the record, I'll show you these solutions. So here is the velocity field. It's very complicated velocity field. The main point that you can see that how it depends from the rotational angle, and the velocity field is a sum of the Hubble term and the rotational term. The rotational angle is defined through the angular velocity, where this R scale is a time-dependent scale. It is an average rotational scale, and the scales are actually this X, Z, and here you can see the Y scale. These are time-dependent function. These are the scales of the expanding fireable, expanding ellipsoid. Okay, so here is the solutions. You can see the particle density, the scale variable, and here are the temperature, our ansatz for the temperature, and this long equation is the energy conservation. We assume this form for the temperature because we wanted to find such a solution that here is a term. So the temperature is a product of the perfect fluid solution and the dissipative correction. The dissipative correction is this G function, and the energy conservation is returned to this G function. In the energy conservation, you can see the effect of the bath viscosity, the effect of the shear viscosity, and without rotation, and the effect of shear viscosity with rotation. So actually, if we have no shear viscosity, then the effect of the rotation is cancelled from the energy conservation. But it will appear in the Euler equation, of course, where this CE parameter is just an integration constant from the condition of the scale functions. Yes, we provided so we examined the asymptotic behavior of this solution if this integration constant is 0, but because of lack of time, I skipped that, and I skipped to the summary, where I just want to highlight the two main conclusions of my talk. So we have found two relativistic dissipative solutions, one for the Navier-Stokes theory and one for the Israel square theory. These exact solutions tend to the Churgo-Cherny-Podama perfect fluid solutions. And the main point that according to these solutions, maybe because of the Hubble flow, we cannot decide from final state measurements that the medium evolved as a perfect fluid with a higher initial temperature, or as a viscous fluid with lower initial temperature. And thank you very much for your attention.
Okay, thank you very much, Gábor. Okay, now questions. So a lot of the discussion were already done in chat box, but it seems to be done. Aha, but Pasi, you have a question. Okay, please.
Navier-Stokes results. You had initially increasing.
Pasi, could you speak up, please?
I'm trying to. Can you hear me?
Not really.
Yes. Oh.
Wait. So my question was that when you had your Navier-Stokes solutions, you had initially increasing temperature. Have you checked how the total energy in your system behaves in that case?
Not yet.
You had better. I hope that you are not violating conservation laws.
Okay.
Yes. So this
Okay.
is take this as a comment.
Okay, thank you.
Okay, all right. So the next question from Masoud, please.
Thanks. Thanks for the great talk. Actually, I have also a comment about the previous question. This is a very typical thing that happens in the Navier-Stokes stories, the reheating effect, and it's not actually physical. But I wanted to ask if you have if you tend the bulk relaxation time to infinity, what happens? Like near the critical point.
I think we didn't examine this question, but Tamás, am I right? Is Tamás here? My supervisor, but I think
just let us postpone to the discussions to the coffee break. But the key point is that we have investigated what happens in the non-relativistic limit, and we found the problem with the Israel steward that it does not reproduce the non-relativistic Navier-Stokes equations because there is this extra constant. If you put that extra constant to 0, then the non-relativistic limit is okay. But if it's infinity, then we have to study it separately.
Thank you.
Okay. All right. Thanks for the comment, Tamás. The next question, Adam, please.
Hi. Thanks for the talk. I really don't know much about this field. However, I heard time to time about this hydrodynamic attractors and stuff, but I guess there they have the connection between hydro and kinetic theory. However, when you show the solution with the viscosity, it ended up with the idle hydro. And is there a connection or something what I should remind myself in between these two phenomena?
Between which phenomena?
Between the attraction, what you saw to the idle hydro solution, and in between this hydro attractor, what people see in kinetic theories.
Can I help out, Gábor?
Of course, yes.
Thank you. So the point is that there is a deep connection which is not yet fully understood. But the first rotating solutions, or the first solutions belonging to this class, were first of all, the Zimanyi Bondorf-Werthmann solution is part of this class. But so that was the first. But what we found was with Béla Lukács and Péter Csizmadia was a totally collisionless solution. Spherical, Gaussian, non-relativistic, homogeneous temperature. And if you put it to the collisionless Boltzmann equation, it turns out that the phase space distribution remains locally thermalized. So it is a hydrodynamical solution too. And then the first rotating solution of relativistic hydrodynamics was found by Marci Nagy during his PhD. that I supervised, and this was investigating the question: are there common solutions of the collisionless Boltzmann equation and the hydrodynamical equations? Even a rotating solution was included. I don't know the deeper connections, but it seems that the perfect fluid solutions seem to be the attractors for late times, even for dissipative hydrodynamics, and it is easy to understand why. For example, if you take a rotating ice skater, pulling it the arms, then it rotates quickly, but when it extends the arms, it slows down and rotation stops. And this is the effect why the Hubble flow becomes the attractor at late times. It is a small system that explodes in 3D, and then the explosion slows down the rotation. And somehow it seems that the common solution of the collisionless Boltzmann equation and the hydrodynamical solutions is also an attractor. But there are a lot of deep things that should be studied here. So I think a topic for the next Zimanyi school.
Thank you.
Okay, all right. Any further questions and comments? I got something in the chat box. Okay, Peter, I guess this is a comment to, okay, not to the speaker. Or do you want to add something in general?
The speaker, but it was answered by Mate and also the other comment.
Okay, good. All right, so I see no further. Tamas, your hand is still up. Do you have any further comment?
Thank you. There was one more point that so these solutions work with homogeneous as well as fluctuating initial conditions. But the key point is that so what people usually numerically do not find easily is that what is the relation between the initial conditions and the dissipative coefficients that lead to exactly the same asymptotic solution. And we have exact results for that in certain cases. And the main point is that there is a huge range of the initial conditions that goes to the same attractor. But if you start from a given initial condition and vary these coefficients, they go to different attractors. And so if you imagine that you know the initial condition and you know the dissipative coefficients, then yes, the final hadronic state is sensitive to this. But once you just focus on the attractor, you can find that several initial conditions and several dissipative coefficients can lead to exactly the same result. So it's very similar to the plots that Masoud showed. Thank you very much for this.
Okay, thank you very much. So Gábor, thank you very much for your nice talk. And let's thank all the speakers this session. Okay, now we have the coffee break. Mate, do you have any announcement?
No, all is well.
Oh, okay, so just like in the schedule, the morning session will start at 11 a.m. In Budapest.
Thank you.
Okay, bye for now.
Bye.
Hi, Mate, if you are around, can you make this breakout rooms?
Yes.
Thank you so much.
Should be done.